Hello everyone, welcome to our ECE6775 final project presentation. In recent years, there has been a significant increase in funding and development for special purpose hardware accelerators. However, the manual design process for these architectures can be time consuming. High-level synthesis helps us by automating this design process, and there are multiple tools that are available to designers, such as AMD Vitis and Siemens Catapult. Throughout this project, we specifically looked into Allo, a Python-based framework that targets spatial accelerator designs and compiles them to FPGA RTL. In an attempt to make Allo more versatile, we extended its capabilities to target the ASIC flow as well. We introduced our final project, ABAX, ASIC Backend for Allo and XLS. XLS is an HLS tool presented by Google that generates Verilog and System Verilog for ASIC design. ABAX introduces a new backend that converts Allo's domain-specific language into two XLS-imported frontends, DSLX and XLSCC. Here we show the flow of Allo frontend outputting Allo intermediate representation, then this IR enters ABAX. Then ABAX can generate DSLX and XLSCC. Finally, Google XLS will take these two supported front ends and generate Verilog. This dual approach allowed us to explore different synthesis flows, ensuring Allo designs can be effectively compiled to ASIC RTL.
For this presentation, we'll be looking at one motivating example of vector-vector add, which is a toy kernel we picked to measure the capabilities of both of our backends. We chose this micro benchmark because it uses memory without any complex read after write dependencies, it requires control flow, and its different parts are representative of a wide range of applications. So first we'll look at DSLX, which is the officially supported front end of XLS, which is described as a Rust-like data flow-oriented functional language. It's based around communicating sequential processes, or procs, for stateful representations, and it automatically pipelines the data paths it generates. A few of its limitations is that there's no supported notion of memory. Any array inside of DSLX gets turned into a large register file. There is no control flow. As seen in this excerpt from the reference, the XLS compiler will automatically unroll every for loop. So DSLX is supposedly an HLS, but it really is an abstraction over RTL. Looking at resolving some of these issues in order to take Allo and turn it into DSLX, we look in detail at the proc. So on the right, you can see at the top of a proc, you define input and output channels, which are val-ready interfaces. Then you initialize some state, and then following that, you have a loop where you keep going every cycle over that state. You take that state, with that state, you do something in the body, which is your data path, and at the end, you compute the next state, which is then used on the next iteration of that loop. So our lower will use these in order to take memory and map it to channels, creating one channel, which is an output channel for the request, and one input channel for the response of that memory. It'll take control flow, like for loops, and map it to that state. In a sense, we're doing manual binding and scheduling. Another issue we consider is that Allo is very much made for C++, and so it uses memref for all of its memory and accumulators. And in order to map the accumulators to state, we need to be able to distinguish what is memory and what is an accumulator. Looking in more detail at our compilation flow, we can see we start with the Allo MLIR. Then we first determine whether what we're reducing is combinational or stateful. If it's combinational, we detect all of the inputs and then all of the outputs by looking through the MLIR. And then once we have that, we're able to set up input and output channels for our proc. Once we have all of that set up, we can emit the entire next function by taking each line of MLIR and turning it into a corresponding line in DSLX. If we have a stateful abstraction, this process gets slightly more complicated, where first we must detect if we have any memory, and if so, we must set up the appropriate request and response channels for that memory, as well as a go and done stream. We also must analyze any loops to figure out which variables we need to store in state, such as accumulators or loop variables. Once we have all of that figured out, we're able to emit next using the same instruction emitter. The entire Allo DSLX flow looks at the bottom. We take the Allo Python, and then we turn it into DSLX codegen. Finally, we interpret that to check its validity, and then we test it, as our framework can automatically generate DSLX tests from Python. Once we have that, we turn it into the XLS IR, we optimize that, and finally, we're able to generate Verilog. Here we can see an example of that. On the right, we have our VV add in Allo. We build that with XLS, then we interpret it to make sure it's valid DSLX. We make a NumPy array in order to test it, and finally, we run it through the entire XLS flow of making it IR, optimizing it, and then turning it into Verilog, where we can optionally specify the RAM latency and the number of pipeline stages. Equivalently, you can specify the cycle time and have it automatically generate the number of pipeline stages. We support a variety of Allo features, namely loops, both unrolled and pipelined, memory, common data flow and floating point operations, but there are a few limitations. Since our lowering is custom, it's limited in the instructions it can lower. It's limited to single function lowering. It's unable to deal with complex control. For example, if you have multiple for loops in a function one after the other, and it's unable to deal with read after write hazards. Now we can see here that code we had before gets generated to this DSLX. So you can see at the top, we have different request and response streams for the memory, as well as a go and done channel, like that of AP go and AP done. Then we have our next function where you can see we first read A and read B by constructing memory requests. We do the addition, then we write the output value to C. And then finally, at the end, we update our state, whether we're done and what the next index we're going to be adding is.
We now discuss the C++ backend for ABAX. The backend has four main components. It has a backend driver that manages all the other parts. It has an emitter that generates basic C++ code, and it has a wrapper that takes that basic C++ code and adds the channeling and the top level module to it to get a final result. And also there's an error handler that looks for things that we do not support in the MLIR and then returns an error report to the user. So the flow is illustrated on the right with the backend driver giving the lowered MLIR to the emitter, the core C++ going from the emitter to the wrapper, and then the full C++ test block being generated and given to the user. And in the case where something is broken, we go through the error handler. We now transition to a demo of the C++ backend. So this is the ABAX C++ backend demo. And as you can see here, we start off with the vector add Allo file, and we build to the XLS target backend. Now, we have one flag called the use memory flag, and you can set it to true to use the XLS memory interface. Now, when we run this code, what we'll see is we'll first see that the code gets lowered to an MLIR, and then from there, we generate the C++ code for the XLS frontend. Now, if we set the flag to false, then we will not use the memory interface. Instead, we'll use C-style arrays, which then get converted into registers in the XLS flow. If we do set the flag to true, then we will use the memory interface support, given to us by XLS C++. Now, going to the XLS, what we would do is we would first take the C++ file and lower it to the IR that we want. And this goes through two steps. Now, if we look here, we have our vvadd opt IR. And from the vvadd opt IR, we can generate the Verilog file. If we look here, now we have the vector add Verilog file. And we can make sure this is the case by quickly looking at it. And this is indeed system Verilog for vector add. And this is what we then use in our PNR later on. From the demo, we see the features that our backend supports. Here, we list them all out. We generate include statements, fixed integer arithmetic, input and output channels, for loops, unrolling and pipelining pragmas for those for loops, and also the top-level pragma. We note that for for loops, you must use a pragma. So by default, we use unrolling if it's not a channel access, and we use pipelining II equals 1 if there is channel access. Just like with the DSLX implementations, the C++ implementation also has limitations. We're currently working on the memory support. And so any data array that currently gets passed into the function is turned into a cluster of registers. We also cannot handle floating and fixed point arithmetic. We're limited to single function lowering. And finally, we have no synthesis integration. So a user must manually copy the C++ code and then run the XLS flow to get the ASIC Verilog. This differs from the DSLX limitations that Zafan talked about earlier.
Since the main purpose of ABAX is to generate synthesizable ASIC RTL, we push things to the flow from Allo to the rudimentary ASIC synthesis and place and route flow using commercial tools and an open source PDK. This allowed us to verify that the RTL produced by ABAX can successfully pass through a commercial ASIC toolchain without any issues. These images show the final layouts for the DSLX generated for vector add and the XLSCC generated vector add designs. One result that immediately stands out is the dramatic difference in implementation cost. roughly an 11 times increase in area and almost a 10 times increase in total power for the XLS CC version compared to the DSLX version. The reason, as Anthony mentioned earlier, is that XLS CC currently does not support memory constructs. As a workaround, the tool uses a very large cluster of registers, and this massively increases both area and power. In contrast, the DSLX flow allows external memory such as SRAM to be connected directly to the VVAD model. As a result, this model is much more power efficient and smaller.
So for a more complicated example, we wanted to also support lowering the systolic array setup we discussed in class for matrix multiplication. To do this, we extended our DSLX implementation. So this involved having the systolic array as well as the processing element. In the systolic array, we determine the processing element grid size based on the loop bounds, and then we create the matrix multiplication structure and setup that allows us to do this. So this involves actually instantiating the various processing elements necessary in the systolic array, creating internal channels, and linking them up. So for our implementation, we're able to pass inputs from the top side and the left side, and it proceeds rightwards and downwards. At the very last cycle, the output is taken from an extra channel in the processing element and aggregated together to create the final result. This is currently the only pattern that we support, but we're able to do this for any matrix sizes, as well as any numeric type supported by our DSLX lowerer. And as you can see, we were able to go through the ASIC process, and our picture and numbers are on the right side. And we want to give our special thanks to Professor Zhang, Nian Song, and Hong Zheng for their help throughout this project. And thanks for listening.